Hello students, in today's Calc class we are going to be working on velocity and other rates of change. So let's get started. First, let me have you try this warm-up problem. This would be a perfect time for you to pause your screen and try this on your own. Hopefully you've paused your screen and you're just coming back to check your answers now. So, all we're asked to do here is find the first and second derivatives for h of t. So we know that the first derivative of a constant is just 0. And we know that derivative of 12t just becomes 12. And we know that this becomes negative 9.8t. So the second derivative is going to be equal to just negative 9.8. So let's move on. So like I said, we're going to be looking at velocity and other rates of change in here. So this is where we get to use a little bit more of the application for derivatives in real life problems. So just a quick reminder, when we want to look for a rate of change, we're basically finding the derivative. Now we don't have to use this long formula anymore, but when we find the rate of change, we're finding the instantaneous rate of change, which means the rate of change or the speed at that specific point. So, example 1, find the rate of change of the area A of a circle with respect to its radius r. So when we see problems like this, we always want to start off with the formula. So it says A equals pi r, or pi times r squared. So that's the formula for the area of a circle. Now it's asking us for the rate of change. So as soon as you see rate of change, you want to find the derivative, which means a prime is equal to 2 pi times r. And so now we found the rate of change for the area of a circle. Now it says evaluate, part B says evaluate the rate of change at r equals 2 and r equals 4. So for r equal to 2, our a prime, or the rate of change of our area, is equal to 4 pi. For r equals 4, the rate of change for our area is equal to 8 pi. Now it says, part C says, if r is measured in meters, what are the appropriate units for dA dr? So for this particular thing, it shouldn't make a difference. The appropriate units, if it is in meters, is going to be just basically meters per whatever it is that we're talking about. So if it's in seconds that we're referring to, what's the rate of change for seconds? But for this, it's going to be, for dA dr specifically, it's going to be the change in the area. That's we have dA divided by dr divided by the change in the radius. So let's have you try this U-try problem. So we're going to try and find the rate of change for the area of a square with respect to its side length s. So again, same idea here. We have your area is equal to s squared because they said use s and a. It says find the rate of change. So we're going to find the a prime, which is equal to 2s, and we're going to evaluate for s equal to 3, a prime equals 6, and for s equals 5, a prime is going to be equal to 10. If s is measured in meters, what are the appropriate units? So this should be our rate of change is our area per meter. Change in area per meter is what we're looking at. Next one, calculate the area, or calculate the rate of change of a volume of a sphere with respect to its radius. So remember, the volume of a sphere, the formula is 4/3 volume is equal to 4/3 pi r cubed. So we can find the rate of change, that v prime is equal to 4 pi r squared. So that's how we find the rate of change. Again, we're just finding the derivative. Now, here's the important part that we want to keep in mind. When we look at these derivatives, we're looking at this for the most part as the position or the motion along a line. So think back to your physics class. Our s represents our position. So our s is our position, It's a function of time t. So sometimes they call this your displacement. Now your displacement, which is listed right under, says delta s is equal to f, or the function t plus delta t minus f of t, or your delta s is equal to your s final minus your s initial. This basically finds the rate, your change in displacement. So where you started to where you ended. What's that distance? Now the next one is average velocity. So if you take a look, your average velocity is delta s divided by delta t. Now if you look at the way that this function is written, this is actually your first derivative right here. So your s is your function, your average velocity is your first derivative, and so your instantaneous velocity is that first derivative at a specific point. So remember, displacement is where you're located, your first derivative is your velocity. So let's look at a couple example problems. Now, our motion along a line has two different things to consider, our speed and our acceleration. Our speed is the absolute value of the velocity. So basically, our speed is our first derivative with a certain point t where t is represented by time. Acceleration is the derivative of the velocity with respect to time. So basically, velocity is first derivative, and acceleration is second derivative with respect to your displacement. So keep that in mind. So, acceleration due to gravity, it says near the surface of the Earth, gravity causes objects in free fall to accelerate at a constant rate. So when we look at gravity in the metric system, it's measured in 9.8 meters per second per second. When we look at this in the US system of measurement, it's 32 feet per second per second. So every time we throw a ball up in the air, we throw something up in the air, well, gravity is pushing it back down at these specific rates. So let's look at this warm-up problem. A particle moves along the x-axis. Its position is given by the equation x of t equals 7t squared minus 12t. Calculate the velocity of the particle at t equals 4. Keep in mind when we look at this problem, the function is represented by x of t. That means this is the position of the object as it moves along the horizontal axis. So if we're talking about throwing a football in the air, yes, it's going to go up at a certain height. But this function in particular only measures that value as it moves along the x-axis. So it's not paying attention to how high or how low it goes, but how far left and right it goes. So if we take a look at this function, and we're trying to calculate the velocity, remember the velocity is just the first derivative. So this becomes 14t minus 12, and we're trying to find t at 4. We're substituting that 4 inside, minus 12. This turns out to be 56 minus 12, or 44. So the velocity at t at 4 seconds is 44. Well, because they didn't give us a specific metric or not, we're going to say that this is either meters per second or feet per second. So here's a much longer example that brings this up a little bit more. Now it says a particle moves, let's change the page. Example 4, a man stands at the top of a cliff 45 meters above a river. He throws a rock upwards with a launch velocity of 12 meters per second. The height of the rock above the water is given by s equals 45 plus 12t minus 4.9t squared. Now, let's point out a couple of things. It's probably a refresher from your physics class. Your 45 talks about your s naught, your initial height, or your initial displacement. Your 12 is your v naught, your initial velocity, and this refers to a portion of your gravity. So we have the following questions A through E, and we're going to break them up by slide. So let's go ahead and take a look at that. Now, when we have a rock that is, or the question is, when will the rock reach its maximum height? So let's take a look at its graph. Now it says that we throw the rock from a cliff 45 meters high. So pretend for just a second, here you are, great picture, I know, throwing your rock from 45 meters high. So you're throwing this rock and it's going up, 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 and then it's going to go down, down, down. The question asks you, when is it at its max? And in this particular case, it should be 1.224. Why? Because we looked at the graph and we found that when we throw this rock, that red graph that we have is basically a sketch of what the rock's position is going to look like. And we know it reaches its max at it reaches its max at 52.35 meters high, and it took 1.224 seconds to get that high. So that's what this x and y value represent. That x value, 1.224, is the time it took to reach its max. The y value, 52.35, is the height at its max. So now I've told you the answer, but let's go ahead and prove it just to make sure we all understand. So when will the rock reach its maximum height? Notice it says when. That means how long is that going to take? So we're going to start with our formula. S equals 45 plus 12t minus 4.9t squared. We're going to take s prime to find that rate, or to find the maximum height. So this becomes, it's not 125, it's 12t. So this becomes 12 minus 9.8t is our final answer, or is our derivative. Now remember, when we take the first derivative and we solve it for 0, like we're going to do, 12 minus 9.8t equals 0, this is going to find our critical point. This critical point helps us to figure out what our maximum height is and how long it takes to get there. So if we start solving for this, we get 12 divided by 9.8 equals t. Let's just prove it. If we take out our calculator, type in 12 divided by 9.8, we get 1.2245, which is the same exact thing I showed you on Desmos. So when it asks us how long does it take, we know that it takes 1.2245 seconds to reach its maximum height. Now looking at the next question, it's saying how high above the water does the rock go? Well, we know how long it took to reach its max. Now what we could do is we can take the original formula and say s equals 45 plus 12t minus 4.9t squared. Because remember, this formula gives us our displacement. It says how high or what height is it at. So if we substitute 12 times or our 1.2245 into the equation, you'll find, because we already know what the graph looks like, we know that this is going to be at 52.35 meters high, or 52.35 meters above the water. So when will the rock hit the water? So when will the rock hit the water? We can figure this out, but what I want to make sure we do is, let's look at what this graph looks like again. Now, again, pretending you're standing on this cliff at 45 meters high, which is right above the river. So here is our river. So think for just a second. We're on this cliff, we throw the rock, and it's going to go up and then go all the way down. And at this point, that's when it splashes into the river. So the question then becomes, how long is it going to take to hit the river? So right here, to erase that other part of the blue, we know that it's going to take 4.493 seconds to hit the water, or to hit the river. Now, again, how do we figure this out? Well, looking at the graph, this is the original displacement graph. In order for us to find that height, or how long it takes to hit this, we're going to either have to factor or use quadratic formula. So all those times in 8th grade when you guys were factoring and using zero product property, this is how it's used. We would factor this particular equation and find that at 4.493 seconds, that's how long it will take to hit the water. Now, I'm not going to do that part for you unless you ask me in class, but essentially you either use the quadratic formula, or you can factor this. Either way will work. I will say because the numbers are weird looking, I would probably just use quadratic formula. Now, it's now asking what is the velocity of the rock right before it hits the water. So keep in mind they worded this very specifically. It says what is the velocity? So velocity means rate of change. So first we would find the derivative. (45 plus 12t minus 4.9t squared) s prime equals 12 minus 9.8t. Now it says what is the velocity of the rock right before it hits the water? So keep in mind, right before it hits the water, well, let's go back to our graph. We know that at 4.493, that's when it hits the water. So to answer the question that's up here, we are going to substitute an x value in here. So we know s prime equals 12 minus 9.8 times 4.493. I know that's the same exact value when it hits the water, but this is as close as we can get. We could change some of these values again, but it's just easier to say, hey, it's going to hit the water at 4.493 seconds. But it's not in the water just yet. It's right about to hit it, or it just hit it. And so we would substitute this value in, plug this into our calculator, and get our answer. So I'll leave that for you to substitute into your calculator. Now notice next question. What is the acceleration of the rock? Remember, acceleration is the second derivative. So let's go ahead and take the first derivative. So s equals 12t minus 12 minus 9.8t. S double prime, which is your acceleration, is equal to negative 9.8. So the acceleration of the rock, if you take a look at what we've done, is negative 9.8. Which means this is really just gravity pushing down on it. So the acceleration of the rock is same thing as gravity. And that makes sense because if you consider, we threw the rock up into the air. So think for a second what that looks like. We threw the rock into the air. Went up, went up, went up, went up, went up. And then for a split second it stops when we reach our maximum. And then it starts to fall down. Well, the only thing pushing it down is gravity. That would be very different if we just threw the ground or threw the rock at the water. If we threw the rock downwards, we're pushing down with more velocity, and gravity is pushing down on it too. Which is why, for the original problem, your acceleration is 9.8. If we did it just throwing straight down, it would be different. So a little bit more practice. A particle moves along a line with position s equals, you can read the rest. What is the particle's acceleration? Again, acceleration is what they're asking for. So first derivative equals 3t squared minus 16t plus 7. S double prime equals 6t minus 16. Now they want us to find out what's the particle's acceleration at 3 seconds. So this might help. So velocity, t equals s prime. Acceleration at t equals s double prime. And we want the acceleration at 3 seconds. So we have 6 times 3 minus 16. We get 18 minus 6, or 18 minus 16. which means our acceleration at 3 seconds is just 2. So marginal cost. Marginal cost, let's talk about this for just a second. It says the marginal cost is the cost to produce one additional item. So marginal cost refers to how much does it cost to produce one additional item. Now, if the cost to produce an item is C of X, so the cost to produce an item talks about how much does it cost if we were to, make something or build something. The marginal cost talks about the change in that cost if we wanted to produce one more. So if you take a look at our marginal cost is just the first derivative. It's the rate of change of the original. Next thing is our marginal revenue. Now revenue, remember, that's how much we're bringing in. It's not how much profit we're making. It's just how much money do we make. So if you think of the most current iPhone on average is about $650 to $750. That's their revenue. But the cost to make it, or their profit, is really how much did they sell it for, your revenue, minus how much did it cost to make it. So the marginal revenue we can find by taking the revenue formula and finding its first derivative. So let's look at a couple of problems that look like that. So it says, suppose the cost to produce X computers is given by C of X equals 5x squared minus 12x plus 200. The revenue from selling these computers is R of X equals 5x squared plus 6x. If a company produces and sells 20 computers, what is its marginal cost and its marginal revenue? So if we take our C of X, and we take the derivative of it, that becomes 10x minus 12. Now if we wanted to find the marginal cost, and we're currently selling 20 computers, so we want to know what is the marginal cost to produce just one of those. Now I know intuitively you might want to put in C of 1 or C prime of 1 because I said one additional computer, but we're currently producing 20. So if we want to find the marginal cost of producing one more when we're already producing 20, you substitute the 20 in there. So that's 10 times 20 minus 12. That's 200 minus 12. 200 minus 12 is equal to 188. So the marginal cost to produce one more computer is $188. So the marginal revenue, if they already gave us the formula, we take the first derivative, which means that's 10x plus 6. And if we wanted to find the marginal revenue for one more computer, we again use the 20. So that's 10 times 20 plus 6, which means our marginal revenue is equal to $206. So just added bonus, if we wanted to find the profit from producing and making one more, you're really only looking at $108, or I'm sorry, $18. $18 difference. So in class, we're going to be working on a lot more of these application-based problems, but I wanted to give you the background. We wanted to talk about how we use these a little bit better. But that's all for now. I'll see you guys next time.